So actually, our work hasn't been published yet. We just submitted it very recently, but fingers crossed. Yeah, so thank you all for coming, and I'm very excited to tell you guys today about some recent theory investigations we've been doing, trying to understand and develop a route for doing programmable simulations that are relevant for chemistry and material science on some of the reconfigurable quantum architectures that we've also been developing in parallel in the lab. So this work is a joint effort between many folks. And also, can everyone hear me okay? Is the volume and everything fine?
Yes, I'm just okay to
Okay,
the fact that it's being read.
cool. Great, yeah. So first, I'd like to just shout out all of my amazing collaborators in this project. So this project has been joint interdisciplinary work between both the AMO theory and experimental groups here at Harvard, along with computational chemists from Martin Head-Gordon's group at UC Berkeley. And it's really been in discussion with all of these various groups of people that we've been able to kind of come up with a proposal that we're quite excited about. So, as many of you know, quantum computing has been all the rage these days. Every week, there's a new startup that's trying to claim all kinds of quantum advantages for the different technology that they're trying to build. There's many different things that people say quantum computers can potentially help with, ranging from applications from factoring and search to things like machine learning and cryptography and optimization problems. And these are all very interesting, but the focus of today's talk is actually going to be on the application of quantum devices to quantum simulation. In particular, we're going to aim to study how quantum devices can be used to help solve quantum chemistry and, in particular, electronic structure problems. So, the electronic structure problem is kind of a canonical example of a quantum system that contains many interacting particles. So, in particular, because of the Coulomb interactions between particles, actually being able to solve this problem in generality involves a computation that's classically very expensive. However, in particular, in systems where these interactions are very important and they have strong correlations, quantum devices are kind of believed to be the best approach for being able to simulate these models in a scalable way. Um, Recently, some very nice resource estimates from the Microsoft quantum computing group have actually shown that, despite the fact that these scalings are in principle efficient, the actual costs for running current state-of-the-art algorithms might actually be prohibitively expensive. So, if you guys, for example, look at like the estimates for quantum chemistry algorithm on a mid-sized molecule running quantum phase estimation, you'll see that even on projected future hardware, it's estimated that the algorithm would take on the order of months or centuries just to solve a single ground state energy problem. So, this is quite concerning if we're interested in using quantum computers for quantum chemistry. So we've been very interested in trying to understand, how can we really cut down on these resource overheads and make the problem much more efficient? And in particular, there's three things that really contribute to this very large overhead. The first is the mapping of the quantum chemistry problem to the quantum hardware. In general, is very expensive in standard approach. The second one is actually the algorithm itself. Quantum phase estimation is oftentimes quite expensive. And lastly, there's also a very large overhead coming from quantum error correction. So in our group, we're working to address all three of these challenges. But today, we're going to kind of focus on trying to see if there's interesting chemistry and material science problems that we can solve. And the approach we're going to take is going to be more of a quantum dynamics style approach instead of, full-blown quantum phase estimation algorithmic type approach. It's cool. So I'll pause here for a second and ask if there's any questions. All right. So that's kind of the setting. Quantum chemistry, as currently set up, is a very hard problem for quantum computers. So the approach that we're going to take is to actually try and combine state-of-the-art classical computational algorithms with, near-term quantum devices, and actually try and use recent developments in programmability of these quantum simulators in order to cut down on a lot of these overheads that occur in the mapping, and really focus on developing hardware efficient implementations for near-term devices. So we are kind of proposing to use a workflow that involves both hybrid quantum and classical resources. And the general workflow looks as follows. First, we'll start off by taking a complicated molecule and actually employing state-of-the-art classical algorithms, such as coupled cluster DMRG, in order to take this complicated problem and reduce it to a model Hamiltonian. This model Hamiltonian is going to essentially capture the important quantum phenomena that occur at low energies. Then we're going to take this model Hamiltonian and implement it in the reconfigurable quantum processor. And on the quantum processor, we're going to simulate time dynamics, which is the easiest thing for a quantum processor to do. And we're really going to use the programmability of some new devices in order to try and achieve this. And then ultimately, the quantum time dynamics outputs are going to be fed back into a classical computer, which is going to use significant classical co-processing in order to take this information and turn it into something that is useful for quantum chemistry. So it's really this leveraging classical computer to significantly reduce the required quantum overheads. Okay. So to focus on a concrete problem, we've targeted to start a very general class of spin models. So these spin models contain single-site spin terms, two-site spin terms, and in general arbitrary higher-order spin terms too. And these individual spins aren't necessarily spin 1/2, but can also have spins greater than 1/2. So it's a very general spin problem. And it turns out that spin problems like this actually appear in many molecule-inspired contexts as a good model for materials that have localized valence electrons at low energies. And these spin problems are oftentimes difficult to solve because they exhibit strong correlations. However, they're generally easy to obtain from classical ab initio quantum chemistry methods. In particular, the coupling coefficients can be computed essentially locally, while computing things like a ground state problem involves doing a non-local full quantum computation. And the key benefit of these spin problems over the full electronic structure Hamiltonian is that they have a much more natural mapping onto quantum hardware, which will also help significantly reduce the overheads. So let's illustrate how example molecule could reduce to spin Hamiltonian at low energies. So this molecule is known as the oxygen evolving complex, which is essentially a biochemical catalyst. And importantly, it has 4 metal sites, these 4 manganeses, which have a lot of valence electrons. And these valence electrons are the things which dominate the low energy electronic structure of this molecule. So if you look at manganese in the periodic table, and you count, it has 5 unpaired valence electrons just on its own. Now, in the actual, I guess it has 7 valence electrons if you include the 4 s orbitals. In the actual molecule, you see the manganese is paired up with some of its neighbors. In this particular example, it's paired up with 3 oxygens. So some number of these valence electrons are going to form essentially bonding orbitals with these adjacent neighbors, while the remaining valence electrons are going to be unpaired and are going to form the active degrees of freedom at low energies. Due to exchange interactions, these 3 unpaired spins will essentially act as a collective spin 3/2 degree of freedom at these low energies. And once you have, so here I'm kind of just showing, schematically how you can get an effective spin 3/2 degree of freedom at low energies. And when you do a more careful calculation, you can also go ahead and derive the interactions between these different spins at low energies. In particular, these different spins will also interact with each other via super exchange type effects, and the actual coupling coefficients associated with these spin interactions are computed using state-of-the-art computational chemistry methods. Okay, good. So then, the output of this computational chemistry procedure is some fitted spin Hamiltonian. And, solving the spin Hamiltonian is still a difficult classical task. So one of the kind of key things that we address in this work is we develop a way of actually implementing this very general spin Hamiltonian, which, as you can see, comes from some underlying molecule and as such could have some complicated connectivity and complicated interaction structure. The other thing that we also address in this work is how to take a simulation of this Hamiltonian and use it to read out important and interesting chemically relevant quantities. So how to turn the simulation of this model Hamiltonian back into useful chemical information. All right.
Nisha,
So,
uh,
yeah.
question. So, at the level of Hamiltonian, it is abstract and general,
Hmm.
right? But chemically relevant requires, being sort of concrete. Are you going to, at the
Yeah.
end, give us some, I don't know, numbers, frequencies, or something, about a particular catalyst?
Yeah. So that's a great question. And indeed, when it comes to actually saying chemically relevant, we need to be like precise and think about specific scenarios. So actually, at the end, I'll show some examples where there are particular target problems that are interesting to chemists that are potentially amenable to this type of approach. Yeah, and we'll show how you can actually get out quantitative numbers using these quantum simulations. Now, I guess this is also a good point to say that we're not interested here in solving all chemistry problems because really the goal is to try and reduce some hard chemistry problems to something that's much easier for a quantum computer to do. So in particular, problems related to understanding the low temperature spin structure of a molecule are the problems that we are going to be able to target with this approach. Yeah. And we'll have an example at the end where I also explain how such a calculation would actually be useful in like a chemically inspired setting.
So I have to stay until the end?
If you want the example, yes. Yeah.
I was going to
Yeah.
stay anyway.
Uh, that's good. Yeah. Yeah, but at a high level, it is the spin structure. So anything involving spin structure is amenable to this approach. Yeah. Cool. Thanks for the question, Una. Any other questions? All right. So cool. So this is kind of the setting, and then I guess next we'll kind of dive into some details on how we actually go about our proposed implementation. So the two key subroutines that we're going to assume, which are two arising from like very recent experimental developments. The first is this ability for neutral atom arrays and other quantum processors to dynamically change their connectivity in the middle of a computation. So, in particular, recent work from our group has shown how atoms can be coherently transported in the middle of a quantum computation uh, in order to essentially change which atoms talk to each other dynamically. Um, and this is going to be a very powerful tool for establishing non-local interactions. On the other side, we will also be using native hardware native interactions in order to engineer efficient gate operations, quantum logic operations. And specifically, we're going to be developing multi-qubit gates, which are tailored to specific model Hamiltonians. So here, kind of the idea is to use controllable hardware native operations in order to in a more targeted way, engineer a particular model Hamiltonian. And these are going to be the two key tests, two key subroutines that we use. And together they're going to form essentially a flexible toolbox for realizing, complex non-local spin interactions. So let's see how this could work for a sample pairwise spin-spin interacting Hamiltonian. In practice, the different types of spin-spin interactions can come from different physical processes. So for example, Heisenberg type interactions can come from things like superexchange, while antisymmetric DM type interactions can come from things like spin-orbit coupling. So the specific details of this coupling coefficient will depend on the specific molecule that you're studying, and our approach is flexible enough to kind of programmably engineer these things. So in the first step, oh, and one more thing. So here in this diagram, each kind of cluster of qubits, it represents like a large spin. And if it has 3 qubits, it's a spin 3 half. If it has 2 qubits, it's a spin 1, and so on. So in the first step of the procedure, we're going to imagine using a reconfiguration step in order to pair up atoms from different spin clusters. Then we're going to apply, we're going to pulse our Rydberg lasers in order to generate interactions. And these interactions are going to be carefully tuned in order to realize spin 1/2 interactions that have the right Jij coupling coefficients. So this can be done by individually addressing each group of 2 atoms. And in particular, because we've used reconfiguration to pair up clusters that are potentially far apart, this step actually mediates and generates the target long-range connectivity. However, if you think a little bit more about it, this interaction isn't actually the same as the target interaction because it acts at the level of spin 1/2 instead of at the level of the large spin. So in the next step, we're going to reconfigure the system again, and this time we're going to apply another gate that acts within each cluster. And the purpose of this gate is actually to generate an energy gap between the large spin degree of freedom that comes from the symmetric subspace of each group of qubits and the rest of the system. So this energy gap is going to be what essentially protects the spin degree of freedom. And by alternating between these two configurations, interactions between clusters and interactions within clusters, we can engineer using Floquet engineering techniques a unitary that realizes the target Hamiltonian on average. And I'll mention here as well that, in principle, higher order errors in this Floquet engineering can also be controlled and canceled out via Floquet engineering or variational optimization of the parameters associated with this unitary. So, okay, yeah, so I'll pause here again and ask if there's questions on kind of the high level Floquet engineering setting. All right.
So, excuse,
Yeah. Mhm.
so is it how you generate maybe like further, like 3 or 4 body interaction? Is it like, can be coherently generated using this method?
Okay, great question. Yeah. So in this example that I drew out here,
Yeah.
we only were considering pairwise interactions. So we're alternating a 2 qubit gate between pairs of clusters and this gate that acts within clusters. In general, if you wanted to engineer a higher body interaction, during this interaction generation step, you would actually implement a higher qubit gate that acts on multiple clusters at a time, multiple qubits at a time. Yeah. So it might be a little hard to, yeah.
So sorry, go ahead.
So for example, here, there's this 4 qubit gate that acts on 3 clusters at a time and can engineer like a fourth order term directly. Yeah.
So in order to do that, you need an operation that actually does the job of like simultaneously acting on 4 qubits. Is that you're saying?
That's correct. Yeah. That's a good question. Yeah. And so actually that's actually the
Oh,
next step.
okay. Sorry.
Which is exactly a good question. Yeah. So, how do we actually go about engineering these crazy interactions, right? So, we talked about an interaction that acts within like 2 qubits or 4 qubits at a time. How do we find these interactions? So, in order to do this, we're going to essentially do some pulse engineering. So, we work with the Rydberg Hamiltonian because this is the one that we have in the lab and it's the one that we have the most experience with. And if you have a Rydberg Hamiltonian for a group of qubits, it can essentially be written like this. So we work with 3 of the states of this Rydberg atom. 2 of them form a qubit degree of freedom, labeled 0 and 1. And the third one is a Rydberg state that has strong interactions. So in particular, when 2 atoms are in the Rydberg state simultaneously, this costs a very large amount of energy, encoded by this interaction term here. So, this Hamiltonian generates these strong interactions and has some flexible degrees of freedom. In particular, the lasers that we use to drive the 0-1 transition and the 1R transition, um, both can have a variable amplitude and a variable phase. So what we actually have been doing is we've been using pulse engineering techniques, numerically optimized pulse engineering techniques, this grape algorithm, in order to find operations that realize the target gates. So these operations actually we've already used in the lab to do our highest fidelity 2-qubit neutral atom gates to date, and also to do a particular type of 3-qubit gate, what's known as a controlled control Z gate. And in this work, we also go ahead and think about adding additional knobs to this pulse engineering toolbox. So, for example, you can consider simultaneously driving the hyperfine, these qubit transition, and the Rydberg, the 1R transition. And it turns out that simultaneous driving significantly increases the class of gates that we can efficiently generate. And the other extension that we've done is we've also gone to larger numbers of qubits. So beyond just 2 and 3, we've also been studying 4, 5, and 6 groups of qubits all clustered tightly together. So we can also focus on 2 specific types of multi-qubit gates that we use in this protocol. One of them are essentially all-to-all spin interactions that engineer an S² operation within the group of 3 qubits. And the other one is a projection operator, which creates this energy gap that we discussed earlier. And we're going to illustrate this pulse optimization procedure by benchmarking, the optimized gate time as a function of spin size. So the general mantra is that the shorter the gate is, the more sequences you can do before the system decoheres. So you want to be able to implement your operation in as short a time as possible. And when we run this numerical optimization procedure, we find that the gate time actually scales much more slowly when we use simultaneous driving compared to the case where we don't use simultaneous driving, we just drive one transition at a time. And in particular, we see that the scaling with the number of qubits is roughly constant as a function of the cluster size, which is actually an interesting observation that we see numerically, but we don't have a full theoretical understanding of yet. Now, nevertheless, this is still a pretty cool and powerful, way of engineering these interactions, because if you were to compare this with, say, a standard quantum computing 2-qubit based decomposition of these operations, you kind of get this almost exponential scaling with the number of qubits within the cluster. So for example, here we're actually working with a log scale, and we see that these projection gates could, for 6 qubits, require on the order of 1,000 or even more gates to realize an operation here that's only requires a couple essentially like local oscillation timescales. So these these operations that we directly optimize using the native Hamiltonian could potentially provide orders of magnitude speedup for generating complex spin operations. Now, just to illustrate the types of pulses that this procedure spits out, here I've illustrated some pulses for the n=4 case, trying to engineer this spin type interaction. And here we essentially reduce everything to 2 degrees of freedom, the phase of one of these driving the Rydberg transition, and the amplitude of the qubit transition. And we find pulses that are, definitely quite complicated, but still well within reason for pulses that could, in principle, be implemented, using current experimental hardware. Cool. Okay, so any questions on the pulse engineering? All right, so next we can discuss actually kind of how do all these things piece together. So we have the the Floquet engineering approach where you alternate this interaction, this projection Hamiltonian, and then we have the pulse engineering, which allows us to efficiently construct operations to use in the Floquet engineering. So the last thing that we did is we also compared the performance of our approach to an approach that would only use 2-qubit gates for a variety of Hamiltonians that might be of interest. And the first model that we studied actually is a spin 1/2 Kagome-Heisenberg model, which contains qubits on the vertices of a Kagome lattice and has, essentially spin interactions along each of these edges. And we actually found that by grouping the interactions into triangles instead of links, we can significantly reduce the overheads and improve the effective coherence time for a given hardware decoherence rate by a factor of 2 to 3. We also studied two interacting large spins and observed a small but noticeable improvement for two interacting spin 5/2. But perhaps most interestingly is when we studied a very complicated spin 2 interacting Hamiltonian with low order Heisenberg interactions, but also higher order spin-spin interactions, you actually find orders of magnitude improvement. And this is really a reflection of the order of magnitude improvement coming from these hardware optimized multi-qubit interactions. So the key takeaways are that these hardware optimized interactions can provide very efficient shortcuts for some of these spin Hamiltonians, and also that this Floquet Hamiltonian engineering toolbox provides a way of really efficiently piecing together these hardware optimized multi-qubit interactions. All right. So that was quite a lot, quite fast. So I'll pause here again once more for any more questions. But this is kind of the end of like the technical implementation section part of the talk. Okay, cool. So now we'll switch gears a little bit and think about kind of a less AMO question and more of like a, kind of a more of like a problem specific, I'll say many body physics type question, which is how do we extract useful information from this ability to do Hamiltonian time dynamics? So the traditional approach for extracting useful information from a quantum simulation is to use an algorithm like quantum phase estimation. So without getting into too much of the details of how the quantum phase estimation algorithm works, some of you may be familiar with the circuit, but in the quantum phase estimation algorithm, you do a sequence of controlled time evolutions, followed by some quantum Fourier transform, and ultimately measure some ancilla system. And this measurement of the ancilla system tells you about the energy of the state that you started with, or in general, measures the energy of the state that you started with. Now, this algorithm works well asymptotically. It has very good precision as a function of the amount of time it takes. However, it's in practice quite expensive because it uses control time evolution and also requires doing many operations coherently and in parallel. And as such, this quantum phase estimation algorithm is likely something that requires a full fault-tolerant quantum computer in order to work, in order to do well. In contrast, we have our kind of near-term quantum simulators that we already have in the lab. And these near-term quantum simulators very effectively do Hamiltonian time evolution and things like projected measurements. It's actually, one of the things which I know you guys have worked on quite a bit is also studying how the information-dense projective measurements, snapshot type measurements, can really be used to extract much more rich and interesting information about the underlying quantum system. So here, we're really excited about using projective measurements combined with time dynamics as a way of extracting both the energies of the system along with a lot more. And there's actually been some exciting recent works on also using this kind of dynamical snapshot data in order to extract much more information from a near-term quantum simulation. So our approach essentially involves it kind of works around this object that we define that we call the operator resolved density of states. Now, this thing is deceptively simple. It's essentially a density of states. So you plug in some frequency and it gives you like a non-zero value if that frequency is equal to one of the energies of the underlying state. And that's kind of encoded here by this delta function. But it also allows you to plug in different operators. And it allows you to weight different eigenstates by the expectation value of this operator. And as such, by adjusting the operator here, you are able to readily access different state properties. So, you have control over both the frequencies, the energies, but then also more eigenstate information. The circuit that we're proposing to measure the density of states looks as follows. It contains 3 steps: a state preparation step, a controlled perturbation, time evolution, and measurement. And in general, this controlled perturbation is usually a short quantum circuit. So like some single qubit rotations or some controlled single qubit rotations more generally. So what does this circuit do? Well, the purpose of this control is essentially to take the system and do some type of interferometry experiment where you take your initial state, which is your reference state, that's only going to be supported in one eigenstate, and you put it in superposition with a different state, a probe state, that's going to be a superposition of many eigenstates. Then when you time evolve the system, the reference only picks up an overall phase, but each of the components of the probe state evolve under a different phase that depends on the energy of that corresponding eigenstate. And at the end, when you do the projective measurement, you're essentially doing an interference experiment between these two different time evolved states, and the analog of the interference fringes that you can efficiently measure are actually these dynamical snapshots. So these dynamical snapshots provide you access to information about the interference between these two paths. More quantitatively, from this dynamical snapshot data, you can access 2 time correlation functions of the form, CO, R, where R is the initial perturbation and O is some probe observable. And this 2 time correlation function contains components that oscillate at the energies of the underlying eigenstates. So, this is kind of a very intuitive thing for many folks in many-body physics, that the time dynamics of observables contain information about the underlying eigenstates. However, one of the important things to realize is that there's no single observable that contains all of the spectral information that we care about. For any particular observable, we're going to couple to different eigenstates in different ways. Now, we want to compute some kind of unbiased spectral quantity, like a density of states. So in order to do that, we have to do additional kind of processing on top of this. So we propose to use this kind of hybrid classical quantum approach to do this additional processing on top of these simple to extract correlation functions. In particular, this complicated expression actually breaks down into 3 simple parts. The first involves a sum over some set of observables. And one of the things that I won't talk about in much detail right now, but you can look in the paper to see, is that you can actually efficiently compute this sum over many observables using snapshot measurements. So this is kind of using kind of classical shadows type tricks. Then it also contains a part that only depends on 0 time correlators. So these 0 time correlators are going to be efficient to evaluate classically because they don't involve complicated time evolution. And then the last part is going to be this kind of the 2 time correlation function that actually requires the quantum simulator to capture. So the quantum simulator is going to do time evolution and take many snapshots in order to get this kind of time evolution part. And we set up the approach like this because we can show that this procedure is actually sample efficient, which means that we can efficiently get something like the density of states using not too many samples in 2 settings. Either the state prep S and perturbation R have some efficient classical representations. So for example, if you're doing chemistry, something like Hartree-Fock can oftentimes give you efficient classical representations. Or in the case where the perturbation itself is a local operator. So this is the setting that's kind of more familiar from material science, where you perturb a system using some local operator, and this could allow it to access, for example, 2D low energy type physics. And the thing that another thing I would like to highlight here is that really everything in this procedure is done classically, except for the quantum time evolution. So it's really just the quantum dynamics that are providing the additional computational advantage here on top of the classical computer. So, and one last thing. So this time evolution in general will be subject to noise. And noise in general will lead to broadening when you compute the Fourier transform. So we decided to at least characterize this in some simple small systems by simulating, depolarizing channel after each gate. And we were able to essentially fit the effect of, local depolarizing channels after each gate to some simple exponential decay noise model. So in reality, there's additional things that happen on top of an exponential decay noise model. However, this kind of shows you roughly that the primary effect of noise is simply to broaden each of the signal. So for the most part, we'll kind of model the errors coming from, finite coherence time as broadening of each of the Fourier transforms. Cool. So
Question.
yeah,
Can you check the previous slides procedure against physical qubit instead of simulation?
so we can, but we haven't, because this would require like the experimentalists to actually run the whole procedure, and that would be like quite an effort in the next. Yeah, so we have plans to start trying some of these digital simulations on Rydberg arrays. This hasn't been done yet, actually, like any Rydberg array. Yeah, so currently the experiment isn't capable of running these things, and that's why we haven't checked them there. But we do hope to.
What part of the experiment is not capable yet? What part in this is the experiment not capable? Doing the proposed time evolution? Or like I
So
kind of missed it.
yeah. So it's really more. It's like a very it's much more of a practical thing. So like they just
Uh-huh.
haven't ever really run circuits that are of this form. So like
Mm.
these circuits involve doing like sequences of operations, each of which involve different rotation angles and stuff like this.
Mm.
And we just haven't done this in the lab yet.
I
It would
see.
be like kind of a new type of measurement, new type of simulation. So currently, no one has actually done this with neutral atom arrays, and it's one of the
Mm.
things that we're very excited about doing in the near future. Yeah.
Thank you.
Yeah. But yeah, that all being said, I guess in principle, all of the hardware is there. So uh, everything that we propose should, in principle, be doable in the next few months. Yeah. Okay. Yeah, thanks for the question. So, okay, so I spent a lot of time talking about how formally we do the calculations, but now let's see it in some simple examples. So again, so let's again start with a really simple system of two interacting spins. Here we'll think about two interacting spin 3/2, which you can maybe think about as coming from the metal sites of some simple molecular complex. We're going to prepare for our initial state, our reference state, the all-up state, which is actually an exact eigenstate because of the symmetry of the Hamiltonian, and therefore has, known, easy to model evolution under the Hamiltonian. Then we're going to generate our probe states, which are going to have the difficult to model simulation by applying a sequence of controlled single qubit rotations. And we can show that the sequence of single qubit rotations is sufficient to probe the entire density of states. So we here now also assume some reasonable finite noise rate. And when we compute the density of states, we get some spectrum that looks as follows. So the black dotted line corresponds to the simulated density of states calculation, whereas the vertical dotted lines correspond to the exact eigenstate energies, of the actual underlying Hamiltonian. And if you look closely, what you see is that this procedure gets this largest peak very well, but actually it kind of fails a little bit on these final two peaks down here on the left. In particular, these two peaks seem to have blended in together. So this is where actually the ability to measure different observables can really come in to help us. So what we see is that if we measure different observables and actually construct the observables that correspond to projectors onto different spin sectors, then the underlying density of states for each one of these different projection observables now only couples to a single band of eigenstates, and therefore is able to much more accurately resolve the energy of that corresponding eigenstate by because the signal has been significantly sparsified. So in the simple example here, a sparsified signal by using many observables is able to much better couple to and resolve each of the underlying eigenstates. And one of the things that I really want to highlight about this projection case is that this is something that's really efficient to do in classical post-processing. We can very efficiently select the measurements we want to do because we're working with snapshots as our kind of underlying, data that we're processing. However, if we were going to do this in quantum hardware, if we were going to prepare, say, eigenstates of this projection operator in the actual quantum system, that would be much more difficult. Because it wouldn't just involve some, simple change in your classical post-processing code. Yeah. So, yeah, I think really the power of this approach is that you can measure many observables in classical post-processing in order to much better resolve the signal. Now, once you have a nicely resolved spectrum, you can also compute many other things from it just by, again, changing your classical post-processing. So, for example, you can very readily compute something like finite temperature susceptibility by taking this resolved spectrum and weighting different eigenstates based on their energies. Um,
So, a quick
great.
question, like, so you're talking
Yeah.
here, the example is a two-spin system. You had
hmm
a product state of up to the power 6. Why
Yeah.
6?
So this product state up to the power of 6. So this is a two-spin system, but each spin is a spin 3 half.
I see, I see,
So even though it's a two-spin system, it's actually a 6-qubit system.
I see.
Yeah, and when we do our simulations, we actually work with everything at the level of the underlying qubits. Yeah.
Uh-huh.
Yeah, and in just a second, we'll also see a significantly larger simulation
Mhm.
coming back to this original OEC complex. So this is the part where we're actually going to come back and connect it to chemistry now again, finally. So we can
There are
run the same
elements,
procedure on.
there are
We're
elements on
going to
the
try,
side.
yeah. Exactly, yeah. So we're going to simulate these manganeses, these 4 metal sites, and do spectroscopy on this effective spin model that the chemists are able to fit for us. And again, we evolved for long enough such that we can reasonably resolve the spectrum. And we see that there's this kind of low energy cluster of peaks, followed by another cluster of peaks, followed by some, you know, larger chunk. And actually, there's many more peaks that we cut off that correspond to very, very high energy peaks that we don't study in this plot. And we can zoom in to the lowest energy cluster of peaks where we see this type of underlying spin structure. And by using this ability to insert different projectors, we can very nicely resolve, the what's called the spin ladder in chemistry, which is essentially the energies and orderings of the lowest lying spin states of the particular molecule. Now, here we actually see this energy difference appearing again. So the two lowest lying spin states, spin 5 half and spin 7 half, are separated by a really small energy, 0.3 nanometers, or centimeter, wave numbers, I think is what the chemists call it, 0.3 wave numbers. Um, Whereas, the typical energy scale of the terms in the Hamiltonian are like 10 to 30 wave numbers. So, these large interactions have kind of conspired to create a pair of eigenstates that are only slightly separated in energy. And as such, simulating this thing for long enough such that you could resolve this energy difference using something like quantum phase estimation would require, much longer evolution times than what we've simulated here. Instead, here, we just by using different observables can actually independently couple to these two different peaks in order to much more accurately resolve the energies of each of the underlying peaks. Yeah. And so good. So why do we actually care about the spin ladder? Well, so we found a chemistry paper by some chemists, Vera Krewald and her group, where they essentially study this molecule and they study two different structural hypotheses. So, I guess there was some uncertainty about whether or not, this particular ligand, this particular thing that's coupled to the manganese has one hydrogen atom or two hydrogen atoms attached to it. And so what they can do is they can kind of construct the structures associated with both of these cases and then recompute the model Hamiltonian for each of them. And it turns out that the presence of this extra hydrogen messes up the interactions just enough such that the energy of this lowest lying spin structure completely flips. So now the lowest energy state is actually 13 halves, whereas the going all the way up to 5 halves. Now the spin ladder can also be measured experimentally, and experimental measurements essentially show that the spin 5 half is the ground state that they see. And what this tells you is that this hypothesis without the hydrogen is much more likely than the hypothesis with the hydrogen. So you can kind of see here this pipeline where a chemistry question is asked about structure, and quantum computation could potentially be used to help assist. Now, of course, everything here is done on a classical computer because the problem is still small enough, but it's supposed to illustrate the kind of general idea.
Sorry, I was a little lost. There was an experiment somewhere, and so the structure, there are two candidates, and the two candidates can be discerned using the delta E ladder, and that was measured experimentally.
Yeah. So okay. So this experiment is like a chemistry experiment.
Right.
So
Right.
like people did actual physical spectroscopy, and yeah,
Right.
for this OEC complex, they
Yeah.
see that the ground state is like spin 5 half,
Right.
and then they
Right.
see that there's a low-lying excited state that has spin
Yeah.
7 half.
Uh-huh.
Now in our proposed yeah.
Where do you fit
Yeah, so everything here is done on a classical computer. We're essentially
in? Right.
reproducing a chemistry paper.
Right.
So
Right. Uh-huh.
in the proposed pipeline, you can imagine, the chemist has these two hypotheses, these two structures, and then they compute a new Hamiltonian for each of them. So each structure corresponds to a different model Hamiltonian.
Mhm.
And then the different model Hamiltonian can then be solved on the quantum computer
Mhm.
using the spectroscopy technique.
Mhm.
And for the two different model Hamiltonians, when you compute the spin ladder
Mhm.
on the quantum computer,
Mhm.
the energies of the low-lying spin states, you'll see these two different things. In
Mhm.
one case, you'll see like a 5 half ground state with a 7 half low-lying excited state, all the way up to 13 half. And then in the other case, you'll see, a 13 half ground state with the latter switched. So now 5 half is the highest state.
But then are you
Um,
competing with the chemistry experiment?
so we're not competing with the chemistry experiment. We're essentially creating a prediction that can be checked against experiment.
I see.
Because, even though you have your experiment, you don't actually
Uh-huh.
know the structure. Computing the
Uh-huh.
structure of a molecule, in the environment that it's, doing
I see.
its
So
reaction in
you're
is a
providing
very
that
different.
connection. You're providing the connection. You can provide the connection.
Exactly.
I see.
Exactly, yeah. So we're kind of hoping that tools like this can help bridge like, ab initio simulation with something like experiment. Yeah, exactly. So we're also pretty excited about this tool because it can allow you to go a little bit further. So once we have done this quantum calculation of the low-lying, say spin ladder, we can actually then go ahead and ask more questions about the properties of this molecule. So, like for example, we can ask the question for each one of the eigenstates, which has a particular total spin. What is the total spin just on the cubane part of the molecule? So the cubane is this little cubic structure that only contains 3 of the 4 manganeses. And what we see is that all of this structure associated with the lowest lying group of eigenstates, actually, all of these lowest lying eigenstates have the same spin on the cubane part. It's actually all consistent with the cubane being fully polarized. It has spin 9 half, so the cubane is fully polarized. What this tells us is that all of the structure is actually coming from spin pairing between the cubane and this fourth manganese over here. We can also then look at, say, like the next batch of eigenstates here, and we see that in this next batch of eigenstates, the total spin of the cubane subunit actually goes down by one, which means that one of the spins within this cubane subunit has essentially flipped. So instead of it being now spin 9 half, it's spin 7 half in total. So this is just to illustrate how, once you have your quantum data, you can really ask whatever question you want about the structure of the underlying eigenstates and, really try to probe what's happening at the system in a very microscopic way. So this is almost, going beyond just this connection to the experiment, but also now using this, structure now to learn more about what's actually happening in the underlying molecule. Yeah, cool. So, so what's next? So, one of the directions that we're very excited about pursuing is also 2D materials. So, just kind of as a really simple example of how a similar pipeline can help you extract properties of a 2D material, think about like a 2D Heisenberg model, where if you flip one spin, the spin will evolve in time, and you can measure like a 2-time spin-spin correlation function. And from the spreading of the single spin flip, you can very efficiently extract something like a dispersion. So, before we were talking a lot about eigenstates, but in the materials context, really what you care about is something like a dispersion relation, which also includes some momentum dependence. And that can also be incorporated into this pipeline. So here we're also interested in kind of trying some early experimental demonstrations on a model for the 2D Kitaev honeycomb. So we have a recent theoretical paper where we kind of flesh out the proposal in more detail for this Kitaev honeycomb. And it has, some cool properties such as, gapless chiral edge modes, which we hope to maybe be able to probe. And in the longer run, we're also kind of interested in understanding this tool as a way of exploring things like the phase diagram of complicated and challenging spin models. And here I kind of would like to highlight that there's many open problems that we don't actually know yet. So for example, how to prepare these good initial states for the spectroscopy procedure, and also figuring out like what are the right observables to measure in order to really characterize, a ground state where you don't already know a priori what the type of order is. So, these are kind of some exciting directions that I think are still quite open and interesting to pursue. Cool. So with that, I'd like to thank you all for your attention. And yeah, so to summarize, we have this pipeline where we think about some molecule and map it onto some spin Hamiltonian, and then implement the spin Hamiltonian and ultimately extract chemical properties of some kind by simulating the time dynamics of it. Yeah. And we're very excited about this as like a potentially resource efficient approach for doing useful near-term quantum simulations for problems that are more inspired by quantum chemistry and material science, but aren't solving the entire ab initio, electronic structure problem. And with that, yeah, thank you all for your attention, and I'll kind of just flash some other things that we're thinking about in relation to this work. And yeah, if you guys have any more questions, happy to take them.
Further question?
So I guess everything was a combination of both extremely clear and very confusing.
No, I think people, you gotta wait for a little bit because it's just sinking in.
That's true, yeah.
Um, so, so something that the chemists cannot do right now that you're offering is dynamics information. Is that right?
Yeah, that's totally right. Yeah. We're kind of in a funny situation because the things that the quantum device does most naturally, like
Mm-hmm.
dynamics, is something that chemists actually have a lot of trouble with. And
Mm-hmm.
then things that chemists do really well, like,
Mm-hmm.
approximating ground states is actually something that for us is pretty hard.
Right,
Yeah.
right.
So, there is, I think, this kind of exciting opportunity, which is really trying to understand how we can use what's different about a quantum computer instead of what's better about a quantum
Right,
computer.
right. No, I mean, in terms of strategy, it makes a lot of sense. Um,
Hmm.
so what is the state of art, like what is the status quo or something? What is the current best technique for predicting dynamics? Is it like, is
Yeah,
there absolutely nothing, or is there something that's funny, or I don't know?
yeah. There are techniques. To be totally honest, I don't have a deep understanding of how they really compare,
Uh-huh.
like all the different techniques. I mean,
Yeah.
I think the one that I'm most familiar with, which I think is
Uh-huh.
actually the kind of state of the art for spin
Uh-huh.
simulations,
Yeah.
is like DMRG and matrix product states. Yeah.
Mm-hmm.
Um, and I think, as we all know quite intimately, time dynamics quickly becomes very expensive.
Right.
So even there, they will oftentimes just focus on, like, say, trying to target a low-lying excited state.
Mm-hmm.
Um, and you can do that oftentimes for the first excited state, but that also quickly becomes very expensive um, as you start to go to higher and higher excited states. Yeah.
Right. So when chemists try to make sense of their spectroscopy, which is
Hmm.
dynamical information, what do they do
Hmm.
before you? What did they do? Or do they do still?
Yeah. So there are dynamical techniques. So like the other one that I know is this equation of motion coupled cluster.
Uh-huh.
And I guess I can explain intuitively. They're essentially constructing ansatses for excited states
Uh-huh.
by like thinking about some Hartree-Fock wave function
Uh-huh.
and then constructing like subspaces of
Uh-huh.
Slater determinants
Uh-huh.
near the optimized Hartree-Fock wave function. And they'll optimize things in the subspace and try to get excited states that way. And I think they will say that these things will oftentimes capture like qualitative things okay, but getting quantitative agreement is actually very hard with, yeah,
But for
with most
small
of these
enough
techniques.
system, can't you just do ED, get the full energy spectrum and
Yeah, yeah,
go with that?
yeah, that's right. Yeah. So that's actually where the model Hamiltonian approach came from,
Mm,
because chemists were trying to figure out how to analyze these systems, and so they thought
right.
that they can analyze a bigger system by doing
Uh-huh.
model Hamiltonians and then solving them
Right.
with ED. Yeah.
Uh-huh.
And
So
that's
that's
actually
what,
where our examples come from too.
I see. So then
Yeah.
you have to beat what can be done with ED to,
Yeah,
right? So you have to
that's right.
be,
Yeah.
your spin system has to be large enough, um, to go beyond
Yeah.
what's possible by ED.
Yeah, that's right. Yeah. And I think, as we all kind of have run into probably in different ways, I think as soon as we start looking at like 2D spin models,
Mhm.
the ED very quickly breaks down.
Yeah, but
Um,
then there is a different challenge because ED, yes, breaks down, but your system is finite size.
mhm,
So, I mean, of course, your system will be larger than ED, so that's good.
mhm,
But yeah, yeah, interesting, very interesting. Yeah,
mhm.
very cool.
Yeah.
Very cool.
Thank you. Yeah, it is true. Like so even here, it's some finite system size. So someone could ask, like, does this mean this oxygen evolving complex is solved in some sense, right? Because this model Hamiltonian. But
Mhm.
actually, one of the things that the chemists have told us is that if you want to get things more and more accurately, it's also important to keep adding more and more terms to your model Hamiltonian.
Mm.
So even for this particular system, you can you can add more degrees of freedom and make the model more complicated
Uh-huh.
as another kind of access to make the problem more challenging for ED. Yeah.
That's true.
Yeah.
It's still chemistry.
Yeah.
They need to be accurate. They kind of matter.
Yeah, they do care quite a bit about accuracy and I think energies.
Yeah,
Yeah.
they do. Yeah. It's, what they do actually matter for life, unlike what we do.
Yeah, we're all working towards the same goals at the end of the day. Yeah.
Any other questions? Um,
Just a quick question. Sorry, I maybe I missed this, but you needed to use an entity of states that's resolved by different observables to actually fully resolve the spectrum, right? Do you have a sense of how
Yeah.
many observables do you need? Like if I make the system larger, does the number of observables scale with the system size in some particular way?
Okay, that's a great question. And I can say for these, so these observables that we looked at, these ones, were actually like inspired by symmetry. So the number of observables that you need actually grows polynomially with the system size in order to resolve these particular observables. Um, now, uh, in reality, we're actually computing everything from snapshots, which means that there's certain tricks you can play where you're computing things directly using the snapshots, but you're effectively working with like a very, very large number of observables. So you might be familiar with this fact that like if you measure everything in the z basis, you can actually measure 2 to the n observables in parallel, namely any poly z string. So in general, we're really using these like snapshot efficient observables, these like 2 to the n poly z strings, but we're doing these computations in a way that it's still efficient because it's working with the snapshots as a fundamental object, as opposed to like the like poly operators as a fundamental object.
Thanks.
Does that kind of answer your question? I'm not
Yeah,
sure
yeah,
if
yeah.
that was
Yep, thanks.
cool. Thanks.
Further questions? If not, let's thank Nisha again.
Cool. Thank you all for coming. Yeah.
Thank you. Hope to see you sometime in person.